Salah tentang
Welcome back to the 3-day FDP program by Government Polytechnic College, Perinthalmanna. Welcome to the third session. The third session is on superconductors, a promising energy storage device. It's a great pleasure for me to introduce our speaker, Dr. Subrata Ghosh, an eminent scholar and academician from the Department of Minerals, the University of Manchester, the United Kingdom. He has received his PhD from Homi Bhabha National Institute, Indira Gandhi Center for Atomic Research, Kalpakkam, Tamil Nadu, India, on vertical graphene nanosheets, synthesis, structure of electrochemical performance. His research interest includes designing nanostructures, establishing the structures, property relationship, and implementing them for energy storage, wastewater management, and electrothermal applications. He has received numerous awards and recognition from various universities, such as Outstanding Doctoral Student Award from HBNI, India, Young Scientist Award, Dr. K.V. Rao Scientific Society, India, etc. Welcome you, sir. Over to Dr. Subrata Ghosh.
Oh, hello. Can you hear me?
It's audible.
Hello?
Dr. Subrata, it's audible.
Yeah. So can I share my screen?
Yeah, you please share your screen. It's visible
Okay.
now.
Okay. So good afternoon, and it's my honor to me in this 3 days technical talk arranged by the Government Polytechnic College, and I'm really grateful and thankful for the organizing committee to giving me a chance to talk on my research throughout my research career. And here I am going to talk on the supercapacitor, which is the promising energy storage device nowadays. And thank you for the introduction. As introduced, I am from the research in the Department of Materials from the University of Manchester, and it is actually hard in the England. And can you see my pointer?
Yes.
It is actually, yeah, it is in the heart of the England, or maybe you know about the United Kingdom. And so this is the University of Manchester main building, and they're having a lot of campus throughout the city, and the environment is completely different here. So you can see it if you see some videos on YouTube or somewhere. So you can see that it is in the city, public place, personal house, and there is a building from the university, and there is several buildings for the university in different campus. And Manchester also is well known for its football because of two big big club in football, Manchester City and Manchester United. And maybe you may aware about that football, and I know that Kerala people are really crazy about football. And also here is very beautiful. This is very beautiful city. You can see the greenery, and good places. You can, if you like, you can visit here. Manchester also famous for the first, well known for industrial revolution, and it started from the long back, as you know from the history book. So industry revolution started from this city particularly, and this city also have the symbol of honeybee. Actually, this is a symbol of the universe. This city, because they love to work socially, work together, and that's why they symbolized the honeybee for the city. And that's all about the Manchester, and it is very great. Means I'm grateful that I got the opportunity to work here and different research environment, and I hope some of you will come for your research and you enjoy the city as well as everything. So coming to the talk. So as mentioned, this basically the talk on the supercapacitor. So my outline of the talk is why do we need to store the energy? That is the basic question behind this supercapacitor. So as the name suggests, supercapacitor. So I will introduce first the concept of capacitor, which is textbook knowledge of from class 10 or class 12 student, and then I will introduce about the supercapacitor, and then I will introduce about how this supercapacitor developed. Is, for example, the history of supercapacitor, how it developed with time, and what are the constituent of supercapacitor, and where we are using these devices, and still there is a lot of work has to be done to make it more effective and efficient. So I will talk on the that and the status of supercapacitor, and I will conclude after that. So why we need to store energy? So there is energy. Energy is in various forms: thermal, electrical, and you can. But what we want, that electrical energy, because if you don't have the electrical energy, your home will be in the dark. So you cannot run your TV, you cannot run your fridge. So basically, we need the electrical energy. And also, for example, if you talk with the mobile phone is very popular, or laptop. So we have to store the energy inside the battery. Actually, battery is storing the energy, and how much it is storing the energy depending on its efficiency and everything. Your electronic device is running for longer time and very effectively. Maybe nowadays mobile is becoming very popular to have for this multi-purpose uses, starting from the calling, playing a game, or watching videos. So what we need is that we want to plug in the plug-in to charge it very faster, and we wanted to hold the charge for long time after using this mobile for playing or watching videos or talking or WhatsApp videos or whatever. So what are the source of energy? So there is a basic source of the energy is the coal throughout the globe. And I'm presenting here the US coal renewable energy consumption by source 1950 to 2019 for using the different kind of energy sources. So you can see there is a consumption of coal is gradually increasing and then coming down. And this is coming down the slope because our source for making the energy from the coal is getting down. So we are towards the because we have limited fossil fuels and other natural sources, and that's why we now this supply from the coal is drastically reduced, and also the consumption is reduced from the coal. because we are having alternative sources, which is renewable sources. For example, solar, wind, geothermal, and hydrothermal, and these are gradually increasing because we have to depend on that. Because if you make the energy from a coal, and we have severe amount of pollution, and also we can see the global impact of the pollution, and the ice is melting, and their water level is increasing, and several natural disaster we are seeing nowadays, and there is a lot of holes in the ozone layers, and we are trying to minimizing the pollution such that we can go back to the nature, and we can use the natural sources, and that sources are the wind, solar, hydrothermal, and these are the things. Now a researcher is trying to implement these sources and trying to find out the alternative storage energy and energy management for our future, because day by day our energy demand is increasing, and it is actually accelerating because the number of population is increasing, people's usage is increasing, and you can have a short journey that we used to have Nokia mobile, which is 1100, and it is having we can only talk, and now we are having smartphone where we can do multiple things, and we are also consuming the energy while we are engaging with the multiple things. So that is the important, and that is the necessity that we have to find out the possible solution to store the energy. And so what we want to do is that we want to generate the energy from the solar grid or windmill, and make the power grid to supply the energy for electric vehicle to the home, or power grid or your laptop or computer. And that is the main funda of doing means for this current research and technologies. Here the concept of capacitor comes. So capacitor is long time back, it is invented as a energy storage device. And if I define the capacitor, and also you knows very well that capacitor is a means for simple example is the parallel plate capacitor. So you have two plate which is far away from by distance d, and you are supplying the energy via some power supply to this metal foil, and depending on the polarity, the charges will polarized in the surface of the metal plates. Yeah, and so important parameters are the dielectric and dielectric permittivity, which in sandwich between this metal plate, and if you see and you obviously knows about the capacitance formula, that it is proportional to the conductive plane area, which is A. So larger the area, larger the storage capacity, and also it inversely proportional to the distance between the metal plates or thickness of the dielectric. Yeah. So this thickness of dielectric, how much thin it is, it can store that much high energy. So these are the basic capacitor you might have seen in our daily uses, and you know very well that these are the capacitors are used in the integrated circuit to either pass they're using as a filter, or they're if you want to block the specific type of current, for example DC, it is passing AC current. And if you tune the radio noise and those kind of things, so you can make some LCR circuit, you can make some filter, low pass filter, high pass filter, and many of the uses we are doing using this capacitor. but can you tell what is the range of the capacity, means capacitance of this capacitor? It's basically picofarad, microfarad, or millifarad. So these are the ranges we are having in capacity for this capacitor. So although capacitor can store the charge, but it is storing the charge for fraction of time, right? So fraction means very less. But what is the important of the capacitor is the power density. That means it can deliver the energy very quickly. For example, if you take a camera and if you are flashing the camera, so that time you need enormous amount of charge to flash, and capacitor is doing this job. So, but if you replace the battery with the capacitor store the charge for that much longer time. So basically, the energy density of the capacitor is very low, and it cannot be used as a potential energy storage device. So that's why the concept of supercapacitor come. This is the general Dragonnet plot. It is basically used for the energy storage device and to show the status of the energy storage device. You can see here what I mentioned just a few minutes back. You can see from this curve that your Dragonnet plot is power density versus energy density. So your power density is much higher for the capacitor, but its energy density is very low. But on the other hand, there you can see the battery or fuel cell or gas turbine combustion engine. These are the also energy storage devices which can store very high amount of energy. So energy density is very high, but its power density is now dropped into 3 watt per kg. So that is the means that is pushing or driving us to make a device, energy storage device, which can have good power density as well as energy density. And that's why the concept or evolution of supercapacitor started. Yeah, so it is started with Ledinger, and long time back it is 1745. So they have used glass jar, foil, and brush chain, and then slowly it is moved to the paper capacitor, where uh, two electrode are separated by a dielectric foil, and this is the dielectric foil, and then wrapped up in the paper and rolled it, and then this is the concept of paper capacitor. And with the time there is coming mica capacitor, because electric are getting changed and developed day by day, because we wanted to have higher energy to be stored in this storage device. So the concept is, so it is moving towards ceramic capacitor, and then it is in terms of film or foil capacitor. The concept is basically the same, that your two metal plate and sandwich and your dielectric is sandwiched between the metal plate. And then the 1957 General Electric came with the concept of supercapacitor. Why the term is the supercapacitor actually best known as the electrochemical capacitor, because we are using the electrochemistry and also the concept of capacitor to increase the energy density and storage capacity of this storage device. And day by day we are improving, we are moving towards the with the micro supercapacitor, which is one of the this plenary program, and that miniaturization of the devices. So we have started from the Ledinger, and now we are on the road of micro supercapacitor and developing the technology and performance of the micro supercapacitor. Basically, it can be same, that you can imagine that 20-30 years of 40 years back, the size of computer, now it reduced to such a way that it can be in your table, and which was unimaginable, and that is the fruit of the progress of material science and corresponding technology. And so we are in the world of advanced material and technology and trying to develop the storage and many promising devices such that we can fulfill our demand of day-to-day life. Right? So this I plotted same curve to give some more insight on the supercapacitor. You can see that this is the Ledinger, and this is actually the concept of supercapacitor. There is two metal plate, and inside this is actually, instead of battery, we introduce the electrolyte, which is liquid. So it is the electrolyte. So what is the electrolyte meaning? Electrolyte is a liquid, contains positive ions and negative ions. So we can tune that movement of ion towards the metal foil, and we can store the charges. So that's why this term, actually supercapacitor, is also having another name called electrochemical capacitor, because we are using the chemical rather than the dielectric solid object. Yeah. So why we use the electrochemical means electrochemistry? We were using the electrolytes because you can see, although this image is not that much clear, but I can say that this is your positively charged electrode, and your electrolyte ion is, for example, this is the positive, so these ions will be the negative. So most the negative ions will be polarized or come into contact with the positive electrode, because we are applying the potential voltage. So if you see this is the actually D, what we have formula, capacitance equal to proportional to A by D. So this is the D thickness. So basically what we known as a difference between the metal foil or thickness of a dielectric in the capacitor. But here the D is the difference between the positive ions and the negative ions. So when you use the electrolyte and negative ions coming close into the positive electrode, so in that time your D is basically reduced to the Armstrong order, means 10 to the power minus 10 meter. For your capacitor, if you compare the capacitor, if you consider a very thin foil of dielectric, it can be having can have a range from 1 mm or some micrometer. But here you see it reduced to 1 Armstrong, means 10 to the power minus 10 mm. So your capacitance of the device is drastically increased by introducing the electrolyte inside the two metal electrode, and that's why this supercapacitor is booming today's world. And I will show you the potential uses of the supercapacitor in the coming slides. And you can see this is the research into electrochemical capacitor, and drastically increased with the time. And there is, and I will tell in the next slide class of supercapacitor and other things, how they storing the charge. Depending on that, the supercapacitor is divided in the further categories. So as I mentioned you, two equation, C equal to epsilon A by D. Epsilon is your dielectric permittivity, A is the area of your electrode or metal foil, and D is the thickness of the thickness between the electrode or the thickness of your dielectric for the case of capacitor. But in here in that supercapacitor, this D is the distance between the positive electrode ions and the negative electrode. So basically, this is the constituent of supercapacitor, where you can see the electrode. This is the electrode, and you have electrolyte, and in middle they are having separator. So this is positive electrode, negative electrode. So when you supply the voltage, your negative negative ions will come to the positive electrode, and positive ions will move towards the negative electrode. And that's why it will make some difference between the series of positive ions and negative ions. And they will, here you can get one capacitor, and here you can get another capacitor. So these two capacitor is in parallel. So you are getting higher capacitance from this device, and this is the concept of the supercapacitor. So if you see this C equal to epsilon A by D, so your capacitance is basically depends on surface area. So port distribution means how much ports it will be there. So that very high amount of charges can go there in the ports, and it can access the higher amount of surfaces. And then obviously electrical conductivity, another important features for this capacitor. And we are having some redox capacitance, and I will come to that point. On the other hand, if you see the energy density formula, energy density equal to half capacitance into voltage square of voltage. So instead of increasing the capacitance, if we increase the potential window or voltage of the device, then energy density will drastically increase by 2 order, because it is termed with V square. And basically the potential window here is depends on the electrolyte you are using. So mainly we're using aqueous electrolyte and organic electrolyte. Aqueous electrolyte is basically water based, and in the water, you know, the thermodynamic stability of water is 1.23 volt. So we can go maximum 1 volt for ideal case, for real case, but we can go up to 1.3 volt in ideal case. But real case, we are going up to 1 volt, and because after 1 volt there is some oxygen and hydrogen generation happening, which is damaging the electrodes properties. So we are safely using 1 volt for aqueous electrolyte. But if we increase the potential window, then we have to use the organic electrolyte. Organic electrolyte, what it can do, we are not using the water here. We are using organic solvent and organic solution, where you can go up to maximum 4 volt. So your energy density is drastically increased. But there is a problem with the organic electrolyte. It is not safe. It is having some dependency on the humidity or temperature, and there is a problem of leaking and damaging. So basically our focus on the aqueous electrolyte, and I will show that how the concept of asymmetric supercapacitors came with the use of aqueous electrolyte. And we also can use some redox additives to hasten the charge storage performance. So basically I can come up with the famous formula of Einstein, E equal to mc square. So if you want to get energy, if you design your material, do the chemistry and do the characterization, and try to design the material such a way you can get huge amount of chemistry from the material to have a high amount of energy from your material. So this is in the lab what we are using. This is the auto lab electrochemical workstation, and for lab test purpose, what we are used to do is, this is our working electrode. We are designing an electrode, and we are having some reference electrode which is controlling the potential between the reference electrode and working electrode, and we are having counter electrode where we are measuring the current through the circuit. So basically we having current versus potential. Yeah, and you can see there is a rectangular circle, that this area under the curve is the amount of charge stored in your device. So basically, we are changing the potential and we're obtaining the current. Higher amount of current with the potential window is higher amount of charge storage capacity. And there is a concept of the two different type of capacitor. One is EDLC, electric double layer capacitor. This electric came from the name of General Electric, and he is the pioneer of this work. And when he begins this work at the beginning for storing the charge using the concept of electrochemistry, and that's why the name is electric. Actually, this electric term came from his name. It's General Electric, his famous American physicist and chemist. And another type is the pseudo capacitive. That means its name is pseudo, means it can store the charges and having pseudo behavior. That means almost similar behavior, but its charge storage mechanism is big different. But you cannot identify from its current and voltage profile. Slightly different, but almost rectangular, and that's why name is pseudo capacitor. And also we can have potential versus time plot. Actually, this is you can realize this one because this is charging and this is discharging. So we should have the efficiency is 100% we are trying. So this is the charging time and this is the discharging time. And same things happening for the pseudo capacitive, although it is not following exactly linear. That's why it is called pseudo capacitive in the name. So so it is not exactly like EDLC, but it is following almost some kind of linear behavior. And these are the formula where we are differentiating from the concept of battery, because I here B equal to 1. This is the main factor for differentiating battery, because in the battery also what we are using two electrode. One is positive electrode, another is negative electrode, and in between we are using electrolyte. But there is electrolyte ion is diffusing into the structure and having structural changes and phase transformation. But in case of supercapacitor, there is no phase transformation, no structural changes. There only concept of electrostatic charges on the surface or near surface and redox reaction on the near surface. It is not changing the phase. That's why it is different from the concept is different from the battery. And this is the concept of supercapacitor. Fine. So here I am explaining the much better way the EDLC and pseudo capacitor. So this electric double layer capacitor is basically the polarization and your electrode. This electrode is basically carbon based electrode. And you know, carbon, there is a lot of carbon, various form of carbon, activated carbon nanofiber. I will show some of the images of those material and some carbide derived carbon. And you also know about the graphene. Yeah, and the Manchester University is well known for the graphene because of this discovery of the graphene, and they are calling the home of graphene is the University of Manchester, because it is discovered at the year of 2007 by two scientists in the University of Manchester. Name is Andrew Game and K. Noblesov. And they have shown that thinnest layer of graphite is known as graphene, having very much promising properties in terms of electrical conductivity, thermal conductivity, magnetic properties, and electrical properties, and many things. They are having outstanding property. And so coming back to the EDLC, the electrode is basically having the electrode composed of carbon-based material, and this is the IP plot I just mentioned in previous slide. And this is the pseudo capacitor, where we are using basically metal oxides or conducting polymers. So while charging, they're having redox reaction on the surfaces, not in the bulk. So that is the important, because it is differentiating this device from the battery. So this redox reactions is happening on surfaces. So this, during the charging, lithium oxide is transformed to the hydroxide compound, and during during discharging, the lithium oxide forming lithium hydroxide compound, and lithium hydroxide is forming to the charging to the lithium charging state. So this is the, you can see this is the discharging and this is the charging state. So you charge, then you discharge, charge, discharge. So you will get almost rectangular space, and this circular is represent that there is multiple redox reaction happening in the, during this charging discharging. As a result, almost you are getting rectangular profile of current and voltage. Okay, and now if now it is basically, we have to see this electrode materials. This electrode materials, if as I mentioned, that carbon materials is used for ADLC, metal oxide and conducting polymers is used as a pseudo capacitor. So here, if you compare this capacitance, that means the capacitance is not due to the redox reaction. For the carbon materials is very high, but in the metal oxide and conducting polymers is very low. But Faraday capacitance means charge stored due to the redox reaction is very low for carbon materials, but very high for metal oxide and conducting polymers. If you see the conductivity is again is very low for metal oxide, but very high for conducting polymers and carbon materials. So these are the comparison table where one criteria is fulfilled by the carbon materials and other criteria is fulfilled by metal oxide, but they both having some pros and cons. If I tell specifically that your carbon materials, the metal oxide and conducting polymers is storing 10 to 100 times higher charges than the carbon materials, but carbon materials are very stable, chemically stable, good electrical conductivity, and very high cycle life, and these are the promising features from the carbon materials, which metal oxide and conducting polymers they don't have. So the next research was moved towards the fuse, means making hybrid of this nanostructure. So some of the nanostructure from my research career. So first one, this is the fiber. Basically, you can make carbon nanofiber or nanofiber composite, and we are using some technique called electrospinning. So electrospinning technique we're using to prepare this carbon nanofiber. This is graphene and metal oxide nanorods, which is used by Perinthalmanna technique. And I am sure Dr. A.K. Sigodasan has shown some of the slide that how he has prepared his sample, and this actually you can see the scale is around nanometer. And to see this structure, we cannot see this structure in naked eye, but we can see the structure growth on the substrate. Sometimes if it depends on the color, and what we are doing, we are using electron microscopy to reveal its structure and morphology, because we want nanostructure, because for the nanostructure, as we know very well, that surface to volume ratio is very high, and hence the properties also is impressive than its bulk. And this concept of electron microscopy also, Dr. Sigodasan has explained that we cannot see in our naked eye, so we have to go in the down scale. We have to reduce our resolution, and which is beyond the limit of our eye. So we have taken the microscopy concept, electron microscopy, and we are exploring the material surface, structure, more. using those electron microscopy, and you might have heard about a lot of electron microscopy like scanning electron microscopy and transmission electron microscopies, and then scanning tunneling electron microscopy, and also scanning tunneling, and also we can do some of the optical imaging. And Dr. Sivadathan has done very wonderful work on the light matter interaction, where he can go some beyond some limit to probe the nanowires and those kind of things. So this is we are actually designing the nanostructure, studying their properties, and applying there for energy storage application for my purpose, and involved in many other applications. So main thing is that we have to understand the structure and the morphology and its property, and then only we can apply that material in the different direction depending on this intrinsic properties of the material. Okay, so as I told you that the another component of supercapacitor is electrolyte. Okay, so we have used the VGN is actually vertical graphene nanosheets. As I told, the graphene is a single layer of graphite, and here this VGN is graphene is standing vertically toward the substrate, and we have explored in the H2SO4 solution. Is H2SO4 solution made concentrated H2SO4. We made 1 molar H2SO4 using and we made the aqueous electrolyte, and you can see the area under the curve, and this is very small. But when we use TeBF4, so TeBF4 is the organic salt, and I used in the H2SO4 and combine them, and so we can get higher window and more charge storage capacity. So you can see the window of this VGN is 0.1, 0.15 to 5. So basically the window is 0.6. But for VGN in TeBF4 H2SO4, you can see the window is basically starting from 0.1 to 0.9. So window is 0.8. So it is increased. And then in case of here, we have done some activation and activated to VGN graphene VG, and then we explored the same electrolyte. This is actually organoaqueous electrolyte we named, and here we can see that -1 to 8. So it is increased 0.9 volt. And this image is again the charge storage performance, so means current versus voltage profile of VGN in the organic electrolyte, where we used TeBF4 in propyllocarbonate. This propyllocarbonate is the organic liquid, where you can see there we can get the whole potential window from -1 to 1.6. That means 1.7 volt window we can get. So these are the possible strategies to improve the energy density, because your energy density is depends proportional to the square of potential, potential window. So these are possible ways, but organic electrolyte we are actually not preferring because of safety issue and temperature and humidity dependency of the electrolyte. So we are focusing on the aqueous electrolyte. Okay, so if we want to make the aqueous electrolyte, as I mentioned, thermodynamic window aqueous electrolyte is maximum 1. Means maximum we can go to 1.23, but in real case we are lower than 1 volt. So there is no possibility to go beyond 1 volt. So what the concept is came that you use positive electrode, you use negative electrode, and positive electrode such a way it can for example it can run from 0 to 1 volt, and negative electrode you can work from -1 to 0 volt. 0 to -1. So in that case, you can extend the potential window up to 2 volt and more than that, depending on the also work function difference between this electrode, and you can increase the energy density again because your potential window is increasing. And these are I have listed the series of positive electrode and negative electrode because they are defining based on their performance and their intrinsic properties. So you cannot use iron oxide as a positive electrode. You cannot use vanadium oxide as a positive electrode because they are well known for working in the negative potential window. And these are the positive electrode, manganese oxide, nickel oxide, and those connecting polymers can be used as a positive electrode. But carbon and 2D materials can work for both positive and negative electrode. And so, as I mentioned, this potential window E also depends on the work function. This phi1 and phi2 is the work function of the electron material. So this work function of electron material difference between the electrode, and you having delta E1 and delta E2 from the positive and negative electrode, and then as a result you can go the potential window more than 2 volt. I will show one of my result. So if you see the material, I have listed the work function and material. So zirconium oxide is 4, and this molybdenum oxide is 6.9. But also we should not see only the work function difference. We have to also see how much charge they can store, means capacitance. So, but for example, zirconium oxide is not good for storing a high amount of charges, as well as molybdenum oxide. But manganese oxide, cobalt oxide, tin oxide, they are good to have good amount of charges. In other hand, iron oxide or ruthenium oxide and manganese oxide are also so they're showing high energy storage high storage capacity than the other electrode. So these are we have to see several things and adjust the material to get the best performance from the device. From the research, I am just showing for the example that we have manganese oxide on particle graphene. This is the structure, and here you can see the surfaces, and this is the iron oxide on particle graphene, this kind of structure, and in middle there is a separator, which the use of separator is basically we don't want to short this electrode, this two electrode, and this will be filled by electrolyte. And for my case here, I used N2SO4, and so we soak the separator and use this and drop the electrolyte here, and then sandwich them and make the device. So you can see that PGN and PFG means PGN if iron oxide can work from 0 to minus 1.4 volt, and on the other hand, Miniaturized can work from 0 to 1.4 volt. So basically, for when we combine these two, we are getting 2.5 volt as a result. This is the so what most important part is that you can see here the specific capacitance and energy density. So if you increase the voltage by this, you slowly increasing your energy density as well as specific capacitance. And these are the other things to explore your material and show the performances. For example, cycle life and other things, charging discharging profile. This is not linear, but almost like linear, as here we have used iron oxide, is a pseudo capacitor. So it is not following the linear profile, but it is almost linear profile. So that is the point to say here. And also, I know that you have seen there is a talk by Dr. Dhanasakarana on the 3D printing for different for other purpose. So these are some kind of 3D printing structure, because we are moving towards the micro energy storage device. So these are the microelectrodes is prepared here in the University of Manchester, and this is the interdigitated electrode, and this we can make on the different substrate and flexible substrate, and we can make some we have made some micro supercapacitor using this. So what is the purpose actually? Means 3D printing technology already introduced by Dr. Dhanasakarana in previous session, but here what I want to say, repeat it again for simple example, that we are filling ink. Basically, this is the ink of the material. Means your graphene, it may be graphene ink, it can be metal oxide ink, and then this ink has to be printed on the surface. So I will show the video how we are printing Yeah. So you can see how it is printed. So this we are continuously pressing we are giving the pressure from the top. We are using pressure gauge, and to flow the ink through the nozzle. You can see this is the you can see this is the nozzle. Yeah, this is the nozzle. Right. Yeah, this nozzle, and through which ink is flowing. This is the ink. This is actually syringe. You consider it a syringe and contains ink, and we are giving the pressure very finely, and we can print this electrode in various forms, as I shown previous slide. And you can stack up. You can increase the number of layers, and so this is the way we are making the micro product, micro supercapacitor, and we are using some gel electrolyte to make the micro supercapacitor device. So we are in the advanced technological era, and we are now everything is going towards miniaturization, and we are preparing some micro electrodes for minimizing the size, for getting high efficiency from a device. And so you can see now that Samsung came up with the smartphone which is flexible, and you can wear in your hand as a watch, and you can bend it, you can do whatever the things you want. You can straighten, it's quite flexible, and it can having a lot of promising features. But still we have to work on further to make it commercialize and the concept and the device, but we are in the right track. So this is the slide where I am showing the uses of supercapacitor. Basically, we are using in electric car. So you might have heard about hybrid electric. So we are using commercial bus lines. We're using supercapacitor for hybrid. HEV means hybrid electric vehicle, and this is the journey of supercapacitor and use of supercapacitor in various places. And so this is the fast charging system, because battery cannot do this fast charging. So we are using supercapacitor in the fast charging system. And there is hybrid electric bus throughout the lot of developed Asian countries. They're using hybrid electric vehicle where supercapacitor is being used. And also nowadays in Europe also they throughout the Europe they're using hybrid electric vehicle to basically minimize the pollution and use the green energy technology. Source is the renewable energy, for example solar or hybrid, solar or wind or those things. And so these are the uses of supercapacitor. But so here I can show that what is the status of supercapacitor. So supercapacitor is lying here. I brought back again the Ragone plot to show the status of supercapacitor. So supercapacitor having good energy and power density balance between capacitor and battery, but so it is having higher power density than the battery or fuel cell, and also having higher energy density than the capacitor. But still we have to do more work and improve the cluster's performance. So the goal is this way, that we want to improve energy density and power density further, because supercapacitor still cannot be used as a full-fledged energy storage device. So although supercapacitors is severely used in day-to-day life in the electric vehicle and other things and cranes, and for example, so electric start. So electric start. They're using the supercapacitor to release the charge for at a fraction of time, and it can store higher amount of charge, as I mentioned before. So these are the uses of the supercapacitor, but we are not able to replace the supercapacitor. We cannot replace the battery by the supercapacitor. because the energy, as you see, the energy density is still below from the battery, and so that is the main challenges and problems to use the supercapacitor as a full-fledged energy storage device. And obviously this energy density, as I mentioned, there is a different parameters which is controlling the energy density. And as a material scientist or designing the nanomaterials, we are working on tuning these properties, the morphology, packing density, surface area, making some high electrical conductivity. Also, it should have good mechanical properties, and also it has to be stable for longer time. Otherwise, we have to replace. But supercapacitor is having a good longevity than the battery. So these are the things happened, and this is the status of supercapacitor. But we can see there is a bright future of this energy storage device, and I hope the way the battery we're using day by day, and that's why the Nobel Prize is awarded last year to that American researcher and good fellow. He's really a good fellow, and we can see the future of supercapacitor in the same way that the way we are using battery today, and the dependency on the supercapacitor also will increase, and as we have seen that it is increasing, accelerating with the time. And I really can see the best and bright future of the supercapacitor. So I would like to thank and to the organizing committee of the MMD, and I also would like to thank Department of Atomic Energy, Government of India, for giving me support to do research in the during my PhD period, and then PhD means postdoctoral period. Then I moved to Republic of Korea. I am thankful to Brain Korea 21 plus postdoc for this program. Actually, they are supporting postdoc to do some innovative research in the country, and they are offering good life also, and good research environment. And basically the idea is to improve the today's world, today's energy storage world or materials world. And also I'm thankful for the Ocean Graphite to support me in the University of Manchester for conducting research. And also I am also thank you all student, teacher, and my professor, all collaborator for doing huge amount of research and giving lot of important important results, and which is changing day-to-day life, and day by day we are improving those things. And I would like to thank you, and is there any, I would be happy to answer your question.
Thank you, sir. Thank you for the informative and engaging session. We are truly honored by your presence. Now it's a time for questions. Participants may ask your questions, or you can drop your questions in the chat box.
Hello, Dr. Subrat. Thank you for the informative session. This is Radhikesh. So, I'd like to ask two questions I have. One is like, what will be the typical lifetime of the pseudo capacitors you are like talking about? I mean, it will be like what will be the typical lifetime?
The typical lifetime still actually it is more than 10 years, from 5 to 10 years. But so much better than our battery, because there is a no leakage and no safety issue, because there is a supercapacitor. As I mentioned, the concept of storage mechanism is based on the electrostatic interaction, not the not the redox reaction. So once you do the redox reaction, there is a change in the phase and structure of your material in bulk. So your material is degrading with time in case of battery. But in case of supercapacitor, these things is not happening. So the reaction is happening on the surfaces. Only surface is playing the major role. So material stability is very, very high in this. This is the actual reason.
Okay, so typically it will be like 10 years and all.
Yeah, 5 to 10 years. Yeah.
Okay, one more thing, Dr. Subrat, this separator, probably I missed it while you were discussing, like how crucial it is and what will be the material used and how will you ensure that total isolation is there?
Yeah. So basically, if you don't, I will go in other way around. So if you have if the separator is not doing the job, so it will be short circuit. Yeah. And so this is the one way to ensure that your separator is working well. Okay. So, and this separator, actually we are using some cream, some filter paper. Those are the basically using in term for coin cell devices and the other cells. And but nowadays there is the concept of soft electrolyte, which is we are making PVA, basically polyvinyl alcohol. This is the kind of polymer, and the electrolyte we're mixing and making some kind of gel. So this gel is we are sandwiching between the electrodes. So there is no possibility of short circuit this electrode. So this gel electrolyte will be means it will gel like, so it will make it will keep separate this two electrode.
Okay, so that will be the latest, like solid electrolytes.
Yeah. So nowadays, a lot of work is going on the solid electrolyte, improving the performance further. So basically, there is a several part, for the device. So somebody is working on the designing electrode, somebody is working on the electrolyte. So this is the first area, and yeah, a lot of research is going on. Yeah.
Okay, thank you.
Yeah, thank you.
Dr. Subradhosh, thank you for for giving a wonderful talk. I'm expressing my sincere gratitude, and I have few questions just for academic purpose.
Yeah.
Generally, we know that a capacitor consists of two parallel plates and separated by a dielectric. Generally, we are studied like that. But in case of supercapacitor, you told that we have in between these two electrodes, we have an additional separation. So I am not understood what is the necessity of that additional separation and what is the use of that additional separation and how it will influence the capacity of the capacitor. Just I want to know for academic purpose. That's all.
Okay. Yeah, good question. Actually, this separator, as the name suggests, so it is actually separating two electrodes. So if you make two electrodes sandwich and there is no space between them, so they're intact, and you are giving the supply from outside this two electrode, what will happen? Right? What do you want to make this two electrode separated by means of something? So that is the separator is doing. Separator is not doing any job towards improving the capacitance or improving the. So it is actually holding the electrolyte, because we are using electrolyte separator. So it is holding the electrolyte, as well as it is just a serving as a separator between the separate these two electrode. So it is having no influence on the charge storage performance or capacity. And indeed, it is useful for avoiding short circuit between these two electrodes.
Okay, thank you. I have one more question.
Yes, sir.
Actually, generally, for the supercapacitor, we may have charge storing capacities, right?
Yeah.
So, in case of battery also, we are storing the charges in the battery.
Yeah.
But the energy density of battery is higher than the supercapacitor. So you
Yeah.
told still we cannot replace the batteries with the supercapacitor. But
Yeah.
whatever I understood means a capacitor having a charging and discharging session. So
Yeah.
the lifetime or time constant of the capacitor will be very small. So if you are increasing the energy density also, whether we can replace this battery with a super capacitor, is it possible? If you achieve the energy density equivalent to batteries, is it possible to replace the battery with the super capacitor? Just I want to.
That is the main goal actually for our current research and technology, that we wanted to replace the battery by a supercapacitor, because supercapacitor having good cycle life and stability, and you can so you would like to we would like to change that replace the battery, but as I mentioned, supercapacitor basically using for high performance high power electronics devices. So basically it is for power application, but unable to compete with the battery in terms of energy density, because of this storage mechanism. And so that's why we are developing the electrode and controlling their porosity, surface areas, and those properties, such that we can increase the charge storage capacity to reach the level of battery. But I believe that we will meet that goal.
Okay, I have one more very general question. Why
Yep.
we are using these nanomaterials for making supercapacitor? Why we are not? No, why you are preferring that nanomaterials for this supercapacitor other instead of other materials? Can you share
Yep.
it?
Yeah. So nanomaterials, as we know, the surface to volume ratio is much higher. And nanomaterials, if you make some nano rod or nano wires and anything, so you can accumulate lots of nano wires, nano or nano rods in some defined areas. Yeah. And electrolyte, which is the electrolyte ion, and the electrolyte ion, if you see the radius of electrolyte ion, it is also is around 2 to 10 Armstrong. Yeah. And so this ionic radius has to be compatible with your pore or your surface morphology. And that's why the nanostructure came into the playing the crucial role, that you can tune the nanowires gap or nanowire size or nanorods and the pore areas between with the order of that electrolyte ionic radius.
Okay, thank you, Dr. Supradagosh.
Yeah, thank you.
Any more questions from the audience? The feedback link is posted in the chat box. All participants are requested to fill the feedback form and submit it for your attendance. So thank you. Thank you so much. On behalf of the organizing committee, Government Polytechnic College, Perinthalmanna, I would like to extend our vote of thanks to Dr. Subrata Ghosh for sharing his knowledge on supercapacitors. Thank you. We are very
Welcome.
thankful. Thank you, sir. We are very thankful to our participants who are right now with us in the WebEx platform. We will join you tomorrow at 9:30 with a new session. Stay safe, stay blessed. Thank you.
hello, can I leave today? Can I tomorrow?